Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to outline what is going to be covered in this section. It's a long section, so it's easy to forget what the goal is. Recall that in our earlier studies, we looked at logistic regression for binary classification. This is where you've collected some data, and you're trying to predict one out of two possible labels. For example, we could have the inputs time spent on your site, and number of pages viewed, and we can try to predict whether or not a user will buy something on your site. Remember that what we can do is, with a problem that has only two inputs, we can draw them on a two-dimensional scatter plot. What we can then do is try to draw a line between the two classes, buy and don't buy. If we can find a line that fits between them, we say that the classes are linearly separable. And recall that when we have a linearly separable problem, then logistic regression would be an appropriate solution, since logistic regression is a linear classifier. The last thing to mention here is that we of course are not limited to only two inputs. As you've seen, our e-commerce data has more than two inputs. Of course, data being two-dimensional allows us to make a scatter plot. In 3 dimensions, you can make a scatter plot, but it's harder to see. And as you hopefully already know, humans can't visualize things of higher dimensionality. At the same time, many realistic datasets have hundreds or thousands of inputs, so it's something we have to deal with, at least mathematically. For linear classification in higher dimensions, the thing that separates the data is not a line, but a plane or a hyperplane. The key point being that these things are all straight, as in not curved. With neural networks, we are going to get a little more advanced. We are going to consider the case where the data is not linearly separable, for which logistic regression is not appropriate. Luckily, neural networks are appropriate for this task. Remember that a linear function has the form W transpose X. Anything that can't be simplified into W transpose X is nonlinear. As you'll see, neural networks are nonlinear. We already know that forms like x squared and x cubed are nonlinear, but neural networks are nonlinear in a very specific way. You'll see that they can achieve nonlinearity simply by being a combination of multiple logistic regression units put together. So that's what we are going to do in this first section. I am going to show you how we can form a nonlinear classifier, which we call a neural network, which we can build by combining multiple logistic regression units, or neurons. In my last course on logistic regression, we talked about binary classification. But what happens when you want to classify more than two things at the same time? What if, instead of just predicting buy or don't buy, we want to predict any number of user actions, like buy, begin checkout, add to cart, abandon cart, and so on? Another example might be classifying a car brand based on a picture of a car. There are more than 2 brands of cars in the world, so you need a classifier that can classify more than 2 things. We'll discuss how to classify more than 2 things in the lecture sigmoid versus softmax. Note that you can apply the softmax retroactively to logistic regression as well. Conversely, if you only want to do binary classification in a neural network, then you can just use the sigmoid. The rest of this section will focus on putting all the previous theoretical concepts into code. So we'll first write softmax in code. Then we'll use what we know about softmax and build an entire neural network in code. Finally, we'll apply it to a real-world problem by building a neural network for our e-commerce data. This section focuses on how to do prediction in a neural network. Or in other words, given an input vector, how do I calculate the output vector, and how do I interpret the numbers that come out? As you'll see, the numbers that come out of a neural network represent the probability that the input belongs to each class. In this section, none of the outputs from our neural networks will make any sense. Recall that logistic regression involves a set of weights. And since a neural network is made up of multiple logistic regressions, it also involves a set of weights. With logistic regression, we use gradient descent to figure out those weights. We call this training. And so the 2 main operations we are concerned with are prediction and training. This section will focus on prediction, while the next section will focus on training. After we learn how to train a neural network, the outputs will make sense, but until then they won't. Remember that this is the typical process in machine learning. You first create a brain, but initially that brain isn't very smart because you haven't trained it yet, so the predictions won't be very accurate. So then you do the training. After the training, the brain will be able to make accurate predictions because of the fact that you've trained it to do so. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, I'm going to gently transition you from logistic regression to neural networks. Remember that logistic regression is a neuron, and we're going to connect them together to make a network of neurons. The most basic way to do this is the feed-forward method, which you'll learn about in this class. For logistic regression, remember that what we do is, we have a weight corresponding to every input, and to get the output y, we multiply each input by its weight, sum them all together, add a bias term, and put it through a sigmoid. This gives us the probability that y equals 1. To make a prediction, we just round the probability. Now let's extend this idea to a neural network. Basically, all we do is just add more logistic regression layers. In this class, we'll work mostly with one extra layer, but you can add an arbitrary number of layers. In recent years, researchers have found more success with deeper networks, hence the term deep learning. But the first step, of course, is to add one layer. You see that the calculations are exactly the same. We multiply each input by its weight, add the bias, and pass it through a sigmoid. That's how we get each value at the node z. Notice how W is now a matrix. There needs to be a weight for each input-output pair. So if there are 2 inputs and 3 outputs, then there will be 6 weights in total. Notice how each node at Z has its own bias, B of J. Next, let's talk about nonlinearities. These are what make neural networks so powerful, because they are nonlinear classifiers. We've already seen the sigmoid, but just to review, it's an S shape that goes from 0 to 1. Another popular nonlinearity is the hyperbolic tangent. This goes from -1 to 1. Notice how it's the exact same shape as the sigmoid. As an exercise, try to come up with a mathematical relationship between the hyperbolic tangent and the sigmoid. You should see that the hyperbolic tangent is just the sigmoid scaled both horizontally and vertically. Lastly, we have the ReLU nonlinearity. It just sets anything that's less than 0 to 0, otherwise passes it through. Despite it looking much simpler than the other nonlinearities, this one has been found to work extremely well for computer vision problems. Let's do a numerical example. Our inputs will be x1 equals 0 and x2 equals 1, or we can just express this as a vector like this. All of our weights will be 1 and our biases will be 0. First, we need to calculate the z's. That will give us z1 equals 0.731 and z2 equals 0.731. They are the same since they both take in the inputs 0 and 1 and all the weights are the same. Next, we calculate the output y. That will give us 0.8. Later on in this course, we'll see how to choose the correct weights and biases so that the neural networks we build can perform accurately. Remember that in NumPy, it's always faster to use the built-in vector and matrix operators than it is to use Python for loops. So we can treat x as a d-dimensional vector, z as an m-dimensional vector, and we can use vector notation to calculate the output of a neural network as follows. But we can go even further than this. Remember that we're not going to have just one data point, we're going to have many data points, and we want our neural network to be accurate for all of them all at the same time. So we can further vectorize our calculations by using the full input matrix of data. This is an n by d matrix where n is the number of samples and d is the dimensionality. Because we'll be calculating everything at the same time, z will then be an n by m matrix, and the output y will be an n by 1 matrix. When we do multi-class classification, we'll have k classes, and y will be an n by k matrix. Because all the elements have to be valid matrix multiplies, all the weights need to be the correct shape. Therefore, W is a D by M matrix, the first bias is an M by 1 matrix, or an M size vector, the output weight will be an M by 1 vector, and the output bias will be a scalar. Because you guys already know about binary classification and the sigmoid, this lecture was purely to introduce you to the architecture of a neural network. In the next lecture, we'll discuss how to extend the neural network to be able to classify more than 2 classes.